Okay, now we'll talk about two operations that we can perform on vector fields. Um, they're called curl, and the other is called divergence. And these two have to do with fluid flow or fluid motion and electricity. So these give us two different fields associated with a vector field, capital F. Okay, so if you remember, that was del, or our gradient, is a vector differential operator. It operates on um, on different things, and the definition, let's say, is, let's write down the definition. And if f is a scalar function, it operates on f like this. Okay, now let's use del, or the gradient, on vectors functions. So let's let f be this function, vector function, and P, Q, and R have first parcels that exist on some region that we're talking about. Then we define the curl of f, and the result will be a vector field. As curl f equals the gradient cross f. And we can write that as ry minus qzi plus pz minus rxj plus q with respect to x minus p with respect to yk. Now you don't have to memorize that, and the notation that we can use, although it really isn't a determinant because you're using operators, but you can say that that's equal to the determinant I, j, k of the first partial with respect to x, with respect to y, with respect to z, so those are operators, and then it's p, q, r. So you can think of it like that, although actually that doesn't make sense because you're mixing vectors with functions and differential operators. So just, you can think of it like that. Okay, the other operation we're going to talk about is called the divergence, and here we're going to obtain a scalar field from a vector field, f, and that's called the divergence of f. And that's defined to be the gradient dotted with f. So that's partial of p with respect to x, partial of q with respect to y, partial r with respect to z, and you add them all up. And again, these two are used in the study of fluid motion, electricity, and magnetism, among other things. So some properties we can talk about is that if you take the divergence of the curl, you get 0, and the curl of the gradient of f is 0 if the second partials are continuous. So that also, if f is conservative, remember that means f is equal to the gradient of some function f. Then the curl of f is equal to 0. And if the curl of f equals 0 and f's components, which are p, q, and r, so if and p, q, and r have continuous partials, then f is conservative. All right, those are some properties. Let's look at this. The divergence of the gradient of f is the gradient dotted with the gradient of f. So we can write that as gradient squared f, and those are the second partials with respect to x, with respect to y, with respect to z, and you add them all up. And this is called the Laplacian of f. And Laplace's equation is del squared f equals 0. And if that's true, then f is called a harmonic function. And you can study these in differential equations. Okay, let's go back and talk about Green's theorem. Okay, you have a region D, you have the boundary curve C, and you have F's components are P and Q. And then we know that the line integral around the curve F dotted with R is P dx plus Q dy. We also know the curl of F is Qx minus Py k here, and the curl of F dotted with k dotted with k is 1, so we just have Qx minus Py. So that says we can say that the line integral f dotted with dr is the double integral d times of the curl of f dotted with k dA. So that's our new result. Okay, the reason this is true is because if you do I, j, k, then you have pq 0, since we have no r. Oh, no, we have the differential operators first. And if you do that, that gives you this. Okay, because if you recall Green's theorem, says that that's equal to d qx minus py dA, and that's what that's equal to. So we have a new way of writing Green's theorem. Okay, let's look at how we can use the divergence or how that comes into play. Now we're going to let C, the curve, be a vector determined by a vector parametrically described as x of t, y of t. The unit tangent vector is r prime of t over the magnitude of r prime of t. Excuse me. The unit normal vector n is y prime of t okay, I'll just write it down here. Then we have the line integral. We can write it as the integral from a to b, f dotted with n of t r prime of t dt. This is just ds. Okay. Then that's equal to the integral a to b of p times y prime over r prime minus q times x prime over r prime dt. Okay, this comes because we know ds over dt is r prime of t. Now we're dotting f with n. Okay, we get that. Then this is going to be the integral a to b p y prime minus q x prime dt. Y prime is dy dt. X prime is dx dt. So this becomes the line integral p dy minus q dx, and that is from Green's theorem, double integral px plus the partial of Q with respect to Y, and that is the divergence of F. So there's another way that we can write Green's theorem. Okay, look at some of the example homework problems in the book to see some small problems.